So we started with the memory, we looked at RAM, we looked at how you can read and write to a memory, right? And so basically, whenever you think about interfacing memory, you need to, so always remember when you want to interface a memory, right? You need to, there are multiple things you need to keep in mind, right? One thing is you'll always have to figure out what is the enable process, right? Whenever you have a memory you want to interface with, normally the memory will have an enable pin. So you'll have to first ensure that you give the right timing signal to enable the memory whenever you want to access it. Then you need to have what are no, so if you look at the data sheet of any memory, it will have things like access time, write time, etc., right? And this will be a range. There will be a nominal and there will be a worst case, right? So again, depending on what kind of a designer you are and what kind of a risk you want to take in your design, if you want to be a good safe designer, you would normally pick all the worst cases and use that to design your circuit so that there are no issues. But obviously you can trade off speed for some functionality by moving to nominal. So as you go, so in your first class in digital design, we'll keep everything worst case so that our design is perfect. But then you'll begin to see that whenever we do design, we'll start trading off. Okay, I'm willing to tolerate some error in my output. Can I make it faster? So what normally happens in engineering processes is, generally to get a circuit functional up to 90% is very easy. The large gap from 90 to 100 is the most difficult part of circuit design, right? So similarly, what you'll see is that you'll get a large benefit if you're willing to tolerate some error. So many a times when you work in very competitive fields, when you work in very competitive designs, then the difference between your product and something else in the market will be determined by how much risk you're willing to take or how have you designed the peripherals so that the risk is mitigated, right? So anyway, so when you look at the data sheet, generally those are key items you need to keep, things you need to keep in mind. So based on that, you will have to generate timing signals, right? And you guys also know how to generate timing signals, either using counters, Johnson counters, or regular counters. It's basically a state machine. So figure out what is the timing signal needed, and then you'll also have a system clock, right? So the system clock will tell you how many clock cycles does this access time correspond to, write time correspond to, etc. Based on that, you design your timing signals. Okay. So again, next semester you'll spend a lot of time interfacing a memory with a microprocessor. So you'll get hopefully very thorough with this process. So this is just an introduction to how you start interfacing various components. So now let's think of a block diagram of a simple memory cell or a bit cell. Let's recall what did we say about the bit cell in the last class. So we said that the bit cell can store a 1 or a 0. So it is a 1-bit storage, right? Now why I'm doing this is because now I'm going to discuss how do we connect these bit cells together to form a particular memory. Some of you alluded to it last class saying that, sir, we need to use a decoder, and you're right. So we'll just complete this by figuring out how do I connect these various bit cells to create a memory which takes in a word or gives out a word, right? And when you think about the design, so remember, memory is a very dense circuit. So whenever you design it, when you design the bit cell, you want to ensure that the bit cell is the smallest possible in terms of area, right? Because remember, memory occupies a large part of the chip. So memory occupies a lot of silicon. Whenever you design something, memory, you normally require a lot of memory, especially if you look at a lot of designs today. Almost 50-60% of silicon area is just covered by memory. So so designing memory is important not only because it determines your area, it also determines your power consumption in the chip, right? The more you access the memory, the more power you're going to burn. Also, if you're not accessing the memory will continue to leak current. So all those things impact your total power curve of your chip, right? So you need to keep in mind when you design a bit cell at the transistor level, It needs to have the lowest amount of leakage possible. At the same time, it should be the smallest area, it should be the fastest circuit. So it has all things going which are going to push you in opposite direction. So therefore, you'll see that when you go and work in a company, they'll have different kinds of memories available to you. There'll be memories which might have a faster read. There may be memories which may have a faster write. There may be still other memories which will scale, which will trade off area for power, right? So depending again on where your product is lying, what is your market for your product, you'll have to pick and choose which kind of memory you'd use. Okay. And also we know that if you're going to use the bit cell into your entire large memory, you want to ensure that the bit cell has an enable signal and it has a read write signal, right? Basically, these two signals are used to either enable the bit cell or they're used to tell the bit cell what is it that we want to do with the bit cell, whether do we want to read the data off the bit cell or do we want to write new data into this bit cell. Sometimes this enable signal at the bit cell level, we also call it as a select signal, right? So basically what we're doing is we need a method which will individually pick a particular bit cell. Once that bit cell is picked, then you use a read or write to figure out as to what you're doing with the bit cell. Right? So if you think of the smallest block diagram of the bit cell, again, I'm not going to go into transistor level design of the bit cell. But if I look at the bit cell essentially is made up of one bit input, right? Or let me change the orientation so that I keep it in line with your textbook. Okay. So your bit cell has a select line, right? So this line, when it goes high, enables this particular bit cell. You also have a read write line. So this line again, if it's zero, it's going to allow you to write. So we can sometimes write this bar as a read write bar, right? So when this signal is zero, we are writing to the cell. When the signal is a one, we are reading off the cell. And then we have two ports, an input port and an output port, right? So this covers all the basic functionality of the bit cell. That is, the bit cell has a way by which you can write into it. It has a way by which you can dump whatever data is inside out. It has a way to select it and it has a way to read write it. Right. So now let's think about a case that we want to design a memory based on this bit cell. So what did we say about a memory? If you look at the top level diagram of a memory, now again, let's do RAM again. What did we say? A memory consists of n address lines or k address lines, right? So we had k address lines coming in. N. So if your word length is n, you have n input lines here. You have n output lines here, right? So this memory can be thought of as, if you want to calculate the number of bits in this memory, how many bits are there in this memory? You'd have to unmute and answer.
2 to the power k
2 to the power k is the number of words. How many bits will I
Time
have?
times
into
n.
n.
Times n, right? So this is the number of words I have in the memory, and these are the number of bits per word in the memory, right? So now, what is the intention? The intention is when I present an address to this memory, I should get an output on the output line, right? So when an address is present, the address should, so if you think of the memory design, you can think of this as various words which are stored in the memory. So whenever we visualize memory, we visualize it as a stack of words which are stored one after the other, each with a particular address associated with it, right? And so in DD, you know that suppose I have k bit lines and I want to target 2 par k cells. What is the chip I'd use? So I want a k
Decoder.
is to 2k, right? So I would use a decoder. So what I do is I take a decoder, so this would be a k is to 2k decoder, right? Which takes in k input lines, right? So these are your address inputs. and you have 2 to the power of k outputs. Right? And so if I think of this as an active high decoder, it means that every time an address shows up on this input, one of the lines at the output of the decoder goes high, right? So that line can be now connected to a particular word. So let's now think about a, say, let's use a 3-bit word. So if I want to design a memory with a 3-bit word, which means that my bit cell has to be, my word has to be 3-bit cells long, right? So these are my bit cells, right? And so what I'm going to do is that if I think about it, this line, suppose this is my A0 or my first uh, address. My first address I'm going to use as a select to these 3-bit cells, right? So which means, remember again, the memory doesn't allow you to access individual bit cells. It's allowing you to access only an entire word. So if you think about it, this address line is connected to 3-bit cells. This is your select line. Again, go, let's recall what the bit cell block diagram looked like. It looked like a select line here, a read write, output, and input, right? And now similarly, now let's take about A2, say. So A2 again will be connected to again 3-bit cells. I'm just taking A1, A2, A0, and A2 just because it's easier to draw. I didn't want to squeeze another one there. But you can imagine that these are basically identical arrays sitting next to each other, and I have a 3rd bit cell sitting here, right? Now, now what do I want? Now, this decoder will help me select which word I want to go into. Now, similarly for the inputs, what do I do? Again, the inputs, suppose there are 3 inputs, right? So I will have inputs as D0, D1, D2, say, right? So my inputs are going to be connected to all of my bit cells, right? Along a column. So along a column, I'll say that this is D0, say, this is D1, say, and this is D2, right? So my D0, D1, and D2 will be connected along the column to each and every bit cell. So what am I doing here is the inputs are given to all the bit cells in a particular column. Like D0 goes to all the input pins of the bit cells in a particular column. But because you have a decoder here, at any given point of time, when an address is given, only one of these rows are selected, right? And so this decoder helps you pick which is the bit cell which is actually talking to the output. Now, how do I pull out the output? So let me just change the color. So, so to pull out an output, I know that I need to pull these pins out. So I will pull this pin out, right? I will pull this pin out. Similarly, I will pull this pin out, this pin out, this pin out, and this pin out, right? So this is going to be my output O0, O1, and O2, say, right? So which means that, again, and now how do I decide whether I have to look at the input or the output? I use my 3rd input, which is my read-write bar. So I will have one common read-write bar signal, which will go into the circuit. So let me call it using this. So I'll have one read-write bar signal, which is going to go to all the bit cells connected in the circuit, right? Right. So again, you see, so this is the organization of the RAM. So RAM is basically built up with a bunch of bit cells. And so every bit cell, again, let's recall, every bit cell has a select line, has a read write bar, input and output, right? So you select a particular word using a decoder. So that's why decoders become very important in memory design. In fact, when you start doing circuit level, we'll find that we did a very simple decoder using static gates in this class, but we'll see that there are a lot of very um, interesting designs you can make with transistors for a decoder, and all of them basically will trade off speed for power. So decoder, if you recall from earlier in the class, decoder is a very big circuit. It has multiple stages if you have to implement it using AND gates, right? It has, if you think about the AND gate, ideally you'd implement it using a K input AND gate, but a K input AND gate might be very slow. If my K inputs are like say 10 address lines, right? Then 10 input AND gate is extremely slow. So then you'll implement it in multiple stages. So what you'll begin to see is that this decoder generally tends to be a very, very power hungry, slow circuit. So people have spent a lot of architectures for various decoders are available. So when you do advanced classes, you look at that. So again, so this decoder is helping you select a particular word, and each word has the inputs given from the overall input from the memory, and all the output pins are connected together, right? And this read write bar is going to basically tell the selected bit cell whether we're writing into it or reading off of it, right? So again, now with this in mind, then you have to think, okay, what are the timing signals, right? So again, you don't want to give your read write bar before, sorry, you don't. So the normal order, what we do is we'll first present the address to the chip, ensure that a particular bit line is selected. Before we do that, we'll make sure that if you're writing into this, we'll make sure that the input word is ready, right? And once that is ready, enable the decoder, select a bit line, then give a zero on this signal, and then immediately we'll begin to write whatever is in the input into the bit cell, right? There we don't care about what's happening at the output. Normally, again, if you're a safe engineer, if you're a safe designer, any write operation should be followed by a read operation, right? So if you want to, and why is that? Just you just want to ensure that whatever you have written, you want to confirm. Suppose you're writing 100 into a word, right? You want to confirm that 100 has been written. So normally, if you're writing something, a safe design practice is to ensure that you read it back again, confirm that whatever is written is what you wanted, and move on. Because sometimes what happens is there might be imperfections in the circuit associated with a particular bit cell, right? And or sometimes you might have made a timing diagram or a timing signal which is not sufficient for the entire write process to occur. And so in those cases, always a good idea to check and ensure that what you've written has been, what you wanted to write has been written into the bit cell. So other thing to keep in mind, generally in design, write speeds are slower than read speeds, right? So what we do is we generally don't like to keep writing and reading data all the time. So we'll see that, that's why the multiple algorithms exist, where they try to minimize how much you have to write into a memory or read off a memory, right? So ideally we'd like to read as much as possible from the memory, but not really write anything into it. And if we want to write something into it, we make sure that the write is not part of the critical path. So when we talk about digital design, we talk about a critical path, which is the limiting path of a circuit, limiting path for speed, for example. So we don't want to keep a write operation in the limiting path if we can help it, because that will unnecessarily slow down your circuit, right? So again, generally keep in mind that write speeds are slower, writes are more power hungry than reads. So generally, a write is an expensive process as compared to read, right? So you'll see that a lot of people will try to avoid writing a lot if possible whenever you want to design an operation. Okay. So again, key point I want you to remember is about this decoder, right? So always remember that a memory is organized using a decoder. Now that decoder is going to give you access to a particular word. So if you think about the simplest design for this case to 2K decoder, a simple K is to 2K decoder will be made up of what? How many AND gates? So if I want to design a case to 2K decoder, how many AND gates do I need and how many inputs per AND gate would I need?
2 raised to k AND gates,
Mm,
and each will have k inputs.
K inputs, right? So you see that as I discussed previously, and why is this? Because every minterm, right? The output of the decoder is a minterm. So basically, your AND is going to generate all the different minterms. If you think about k input lines, you'll have 2 to the power k minterms, right? So if you think about a 2 input, you'll have, suppose you say 2 bits, right? A0 and A1. Then we essentially have 0001, 10, and 11, right? So 4 minterms. And all of them will be represented as a 2 input AND gate. First input, 2 input AND gate will have A0 bar and A1 bar. Next will have, so you can think of them in addition, you'll have K inverters also associated with, if you don't have the complement inputs available. So in addition to K input to power K AND gates, you'll also need K inverters to enable to design this decoder, right? So again, so what you begin to see is as you start making the memory larger, right? So remember, as you introduce more and more, as you increase the size of the memory, this decoder starts getting very large, right? So sometimes what we do is, instead of dealing with one large decoder, sometimes it makes sense to break it into a row decoder and a column decoder. So what we'll do, for example, is that we'll break this two-dimensional memory. If you think about this initial design that we just did, right? This initial design is a one-dimensional memory, if you will, because it has all cells arranged in this fashion, right? If you think about the previous, it's just arranged in this fashion. So cell one, cell two, so word one, word through, etc. Now you can also think about a case where I can design a circuit, a memory, I can organize it this way, right? Where I can call this as cell one, this is cell two, this is cell three, and this is cell four, right? And I can use one decoder here. So this would be my column decoder. And I can use one decoder here, which would be my row decoder, right? So the row decoder, so what that means is essentially, if you think about 4 cells, so let's think about 4 cells. If I have 4 words or 4 words I need to write into memory, how many address lines do I need?
2.
Two address
2.
lines, right? So now those 2 address lines, I can either use them as a 2:4 decoder in this fashion, where I take 2:4 decoder, have 4 inputs, and each 4 inputs are given to one of the words here. So I can access all words, or I can break it into two 1:2 decoders, right? Where one is used for a is used for the row decoder and one is used for the column decoder, right? So what happens in this is, it's not very apparent when you use just 4 cells, but you see that all of a sudden, instead of using a 2:4, I've reduced the size of the decoder by half. So that gives you some additional speed. So many times when you think about memory normally today is not organized just like this. It's normally organized as a row and a column decoder. Again, it might be impervious to you if you're sitting outside, and if this is your block diagram of the memory, where this is K and this is N, right? You don't care how the memory is organized inside. So you wouldn't know just based on the top level block diagram whether the memory is organized this way or this way. But I'm just saying that there are 2 different ways to organize the memory. We use this because generally this uses a smaller size of the decoder, so it tends to be faster and with a smaller power budget, right? So you're basically breaking down a 1D problem into a 2D problem. Okay. And the last thing I wanted to remind you about memories is that, suppose, so let me ask you a question. You guys buy or it's all SSDs you have in your computer and all that. So when I say 2 GB memory, how many pixels do you think are actually present in the memory?
2 into 10 power 9.
2 into 10 power?
9.
That is bytes, nah? So bits will be
Mm,
16 into 10 power 9.
16. Okay. So now what normally happens when you buy memories, you'll actually see that the number of bit cells we normally manufacture the memory for will almost be 3 to 4 times what is the memory targeted at. So when you buy a memory, the chip actually has up to 4 or 5 gigabyte of raw memory, right? And the reason we do that many a times is memory by definition, because it's a very device intensive process, it has a lot of failing cells. So whenever we design memory, right, you'll see that the memory will be spec'd for much lower than what it's actually designed for. And the reason is because a lot of testing will happen once your chip comes back from the foundry, because many a times you'll see that the yield on the memory is not high enough. So even though you have 4 gigabytes of memory, it will be spec'd for only 2 gigabytes. And the reason is because memories cells tend, not all of them will work. Some of them will have reliability issues. That is, some of them will stop working in a few cycles of memory, etc. So generally, the rule is that there is a lot of, when you deal with memories, when you start interfacing memories, you have to also worry about error coding, etc. So whenever you write something to memory, when you want to read something off the memory, because of the fact that the memory, see, you're putting data into a particular chip and you're hoping that the data doesn't change as a function of time. But as a good engineer, you should remember that that data can change as a function of time, because of the fact that that memory is continuously being powered by a power supply, and there is a continuous wear and tear happening on the memory. So it is possible that the memory cells, suppose you had initially stored a 1 on the bit cell, it is possible that some of the cells, the ones might flip to a 0, right? And that is, and especially if you've used if the memory chip is old, right? So now normally we spec a chip for say 5 years. So if you're running in your fourth year or third year of operation, then you'll see that the failure rate begins to increase. So generally when we deal with memory, we always deal a lot with error coding. So I'm not going to go into this. You can read up in the textbook about it. But what I want, and this is why we taught you parity and Hamming code and stuff like that in the beginning of the class, that it is the duty of the designer to ensure that the quality of the data remains the same. So when you are storing some data into the memory, you need to also think that how do I figure out if this data is corrupted, right? So whenever you design systems, you need to always keep in mind that eventually you are responsible for your data. So you need to ensure that you have a way to find out if the data is corrupted or not. So a large part of memory usage will also deal a lot with how are you going to look for errors, what is error coding, etc. Right? So again, this is not something we expect you from this class, but keep in mind that these are things you need to think about when you think about memory. Okay. So
Sir,
now let's get, yeah, go ahead.
sir, why is the actual usable memory lesser than what is like mentioned on the spec sheet? Like you said, it is 3 to 4 times like manufactured as such,
Right, right.
but sir, for example, if it's a new 1 terabyte hard drive, then its usable
Huh.
memory is only around 932 GB.
Right. So one is because it also has a bunch of startup programs and all which the memory uses, right? So that is written into that. What I meant is, even if you look at a 1 terabyte memory, if you actually went in and counted the number of bit cells manufactured, that will be little around 2 terabyte. And the reason it is spec for 1 terabyte is because most of them have failed. And so generally what happens is that the yield of a memory is not that high, and the fails happen much later when they go into testing. Now, when you buy a memory, in addition to that, you also have startup programs, you have programs which have their own, if you're erasing, if you're writing it, you need some interfacing programs in addition to, it's not just a bunch of memory, right? You have some interfacing initially when you plug the USB into your board, right? There needs, some programs need to be run on the memory. So all those occupy space in the usable memory. Therefore, the usable memory actually tends to be less than what is spec for. So you do get cheated in that.
Sir, but uh, how are there bit cells on a hard drive? Like, isn't a hard drive like a spinning magnetic disk?
So in a magnetic disk, it is different. There it is, but if you look at SSDs, I mean, nobody uses hard drives anymore, right? So if you look at SSD is nothing but a flash cell. So there we are talking about non-volatile memory. So here I told you was a RAM, right? Non-volatile memories work very different. The transistor used is different. Like in the magnetic, for example, in the hard disk, we use magnetization. So the mechanism of coding, or what is a zero and what is a one, is very different there. What we talked here is essentially an SRAM memory.
All right, sir.
Yeah. Okay, so let's now talk about ROM. So
So,
we went, yeah, go ahead.
so you said SRAM. What does S stand for?
Static random access memory.
So, like, there is a DRAM as well,
Yeah,
dynamic.
DRAM is dynamic. Yes. Yeah. Again, I think you guys will do some of it. I think in architecture, I'm not sure. Hopefully, architecture will cover a little bit more into what is an SRAM, what is a DRAM, when are they used. I mean, I don't have time to cover it in DD. Anyway, let's go to a ROM. So a ROM is a read-only memory, right? So a ROM is organized very similar to a RAM. The only difference, as I told you, is that you can write it only once, right? And so what the way the ROM works is you have fuses or in the memory cell, in the bit cell, right? And so what this does is, initially when you buy a ROM chip, you can program into that ROM chip. Once that program is done, then you cannot reprogram it again. Now, obviously, we have electrically erasable proms now. In fact, for the last 30 years. So having a chip which can write only once is kind of not a very smart design. So people have found out ways where you can erase the entire memory and reuse it again. But essentially, what the ROM means is that you treat it as a component where you either erase the entire memory or use the entire memory as such. So in that sense, it continues to function as a read only. That is, you can write it only once and then you reuse what is written into it many times for your applications. And then later, suppose you want to reuse the chip, you come in with a blank erase, you erase the entire memory and then rewrite into it again and then use it again, right? So the ROM, if you ask me, think of it just as a hardwired RAM for this class at least, right? So what you see in the ROM is a ROM again can be thought of again now, because we don't have inputs and outputs to worry about the ROM. A ROM can be just thought about as k address lines and n output lines, right? Because we don't have the concept of read and write anymore on this ROM. You write it only once. So there's no question of enabling it for write or read. I mean, you have different ways to write and read, but when you're using the ROM, you don't need to care whether it is, because the only way you can use it is using a read signal, right? So you can think of the ROM as k address lines coming in, right? And if you think about the ROM size, you can talk about as n cross 2 per k and n output lines, right? And so what it essentially means is that you basically can program anything. You can write the ROM with any data that you want. But what you see here is this system looks like k inputs and n outputs, right? So if I think of it very it's a very dumb way. If I think about the ROM can be thought of as it's taking in k inputs and giving out n outputs, right? So it looks like a combinatorial circuit. So the reason why the ROMs are used a lot is basically you can dump any combinatorial circuit on it without worrying about gate level design, right? For example, so let's do an example and we'll go using that, we'll try and see how to do it. So here's the problem for you. So design a circuit that accepts a 3-bit number right, and gives the square of the number as the output. So this is the problem given to you, and using a ROM. So first of all, let's think about what is the size of the ROM we need. So again, you don't have to worry about positive and negative numbers. Let's assume these are all unsigned numbers. So we don't have to worry about positive or negative. Okay, so I want to decide what kind of a memory I need to use here. So first tell me how many inputs are there, how many outputs are there here. How many inputs do you need in the circuit?
Three input.
Three.
One input.
Three inputs, right? Three inputs, right? It's a 3-bit number, right? And this is a parallel. We're not worrying about serial inputs right now. So we need 3 bits. So you can think about the input as A2, A1, A0, where A2 is the MSB, A0 is the LSB. How many outputs bits do you need?
6.
Five.
5.
5 or 6?
5.
Five.
5. 5.
49, na?
6. Yeah, 6.
6. Okay.
Right? Now, correct. So now let's think about. So we need 6 because 49 is written as what? 110001, right? So 32 plus 16 plus 1, 48 plus 1, right? So ideally you need a 3 to 6. So if you think about it, you would need, what would your ROM look like? Your ROM would look like a 2 power k times 6, right? So there should be 8x6 ROM you would need. Now let's think if we should use an 8x6 ROM, or can we get away with something simpler? Again, you want to use a ROM which is of the smallest size needed. You don't want to use a big ROM if you can get it done with a smaller ROM. Again, convention is 2 power k times n. So this is how you define the size of the ROM.
So,
Okay. Ha.
so can you repeat like from the start? I think I got lost a little bit.
Okay. So I want to design a circuit using a ROM, right? That accepts. So first of all, do you agree with me that a ROM can be used as a combinatorial circuit?
Yes, sir.
Right? Okay. And how does a combinatorial circuit work? It has k address lines, it has n output lines, right? So all the ROM is doing is mapping a certain address to a certain output, right? So I can think of, so now I want to design a combinatorial circuit here, which has a 3-bit input. So it takes an input A2, A1, A0, which means in binary, this would be from 0 all the way to 7, right? In decimal. And I want the output of the circuit to be the square of the number. So the output has to be from 0 to 49. Okay. So 0 to 49, 49 can be represented using 6 bits, right? So you need at least 6 output lines for the circuit to work. Are you with me so far?
Yes, sir.
Right? So if I just use the dumb previous analogy, I'm saying here that there are 6 output lines and there are 3 input lines. So sorry, I should change this. This should be written as 2 power k times n. So if I had 3 input lines and 6 output lines, the size of the ROM would be 8 cross 6, right? That's all I said
Yes,
here
sir.
is that if I, right? So now let's
Okay,
see
sir.
whether this is the right way or can we get away with a smaller ROM. Sorry, was there a question? Okay, so let's quickly write the truth table for this. So we have A2, A1, A0, B5, B4, B3, B2, B1, B0. Let's call the B's as the outputs. So I have 0, 1, 2, 3, 4, 5, 6, 7, right? 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 101, 110, 111, right? Again, 0 squared output is 0. 1 squared output is 1. 2 squared output is 4, right? So 0, 0, 0, 1, 0, 0. 3 squared output is 9. So 0, 0, 1, 0, 0, 1. 4 squared output is 16. So 16 goes as 0, 1, 0, 0, 0, 0. 5 squared is 25. So 16 plus 8 plus 1, right? So 0, 1, 1, 0, 0, 1. 6 squared is 36. 36 is 32 plus 4. So 1, 0, 0, 1, 0, 0. And 49, as we said, is 32 plus 16 plus 1. So it goes as 1, 1, 0, 0, 0, 1. Right? So this is the truth table of the circuit we want to make. Now we already said that we can do this very simply using an 8:6 ROM, right? But we also see something funny here. If I look at B1, right? B1 is always 0, right? So, and then I also see that B0 is always A0 because B0 just follows A0, right? So if I think about it now, B1 and B0 are not really any logical functions of A2, A1, A0. Like for if I want to generate B0, I can just pass A0 as the output to B0 and I'll be done with it. For B1, I just need to ground the output line. So essentially what I have is I have to map B5, B4, B3 and B2 to A2, A1, A0. So what I do instead is I would say that I would use an 8x4 ROM, right? And how would I use it? Basically, I would write 0 at address 0, 0 at address 1, 1. So you guys follow, right? I'm looking at this part of the circuit, right? So this is my address. So at address 0, I write this word 0. At address 1, I also write 0. At address 2, I write 1. At address 3, I write 2. At address 4, I write 4. At address 5, I write 6. At address 6, I write 9. And at address 7, I write 12. Everybody following? So if I want to draw the circuit now, I would draw the circuit like this. This would be my 8:4 ROM, right? My three inputs are is A2, A1, A0. And my outputs I want to get are essentially B5 to B2. So my outputs are going to be B5, B4, B3, B2. B1, which is my output here, I can just ground it. So that is a 0. And for B0, I can just take output A0. So this is my, and this is my output B0. And how do I define my ROM? I say basically I give the address and data, right? So my address has A2, A1, A0. My data is whatever D3, D2, D1, D0. So the way what I'll do in the ROM is I'll program the ROM this way. As we said, zeros in the first two addresses, right? And in address 2 it is 1, 2, 4, 6. So 1, 2, 4, 6, and 9 and 12. Right? So this is how I would implement this circuit. So what you see is that using a ROM, it's very simple to implement combinatorial circuits, right? So instead of worrying about K maps and stuff like that, all you have to do is write the truth table of the circuit and then load that particular data into the ROM. So once you've done this, all you have to do is anytime now an address is given to this circuit, it's going to give you the square of the number, right? So implementing a combinatorial circuit with ROM becomes very easy. It's just a matter of mapping an address to a data. Okay. Any questions here? We'll do a couple more examples on the tute. But any
How do
questions
we
here?
ensure that once we have written, we can't write again?
That is the functionality of the ROM, right? So the assumption is that once you've written this, it's done. You're not never going to write again into the ROM. In reality, what will happen is there will be a pin which is known as an all erase pin. So once you give a 0 there, essentially you can erase the entire ROM, but we don't worry about that in this class. In this class, we'll assume that the ROM cannot be written. So all you'll do is you'll say write the ROM once with this. Once you're done with that, it becomes a combinatorial circuit. And then you can use it to generate the square of a 3-bit number at any time.
So the 000 and 001 address are going to the same data.
Correct. So what was the question? Can you optimize it more is your question?
Yes, I was just confirming.
Yeah, you tell me how to optimize. Remember, the memory works as an address to data, right? So both the addresses are pointing to the same data. That's all it means. So I don't think you can optimize that further. Anyway, like the point again I want to make is that these ROMs that are usually available in the market are small size ROMs too. So whenever you want, I know some of you have tried to do this in your assignment. So whenever you want to implement a combinatorial circuit, in addition to decoders, multiplexers, right, you can also implement a combinatorial circuit using a ROM. Okay. So with that, I think I'm past 12:50. So what I'll stop here. Tomorrow on Friday, we'll start with the programmable and and or arrays. I think with that, hopefully we'll try to finish some of it at least on Friday.
Sir,
Yeah.
Excuse me, sir.
sir, for
Yeah, one second.
memory,
Huh.
memory, how many bit cells are there?
So, repeat your question again. Sorry, I didn't. It's not audible to me.
Sir, for 2 GB RAM memory, how many bit cells were there?
2 GB.
Yes, sir.
So 1 KB. So 2 gigabytes, right? So
Yes.
1 kilobyte is 1024, right? So 2 power 10 bytes, right?
Yes,
So if you think about 1 megabyte, and then it's 1 kilo, so it's 2 power 20 bytes, and 1 giga will be 2 power 30 bytes.
wait, like 1 gigabyte will be 2 to the power 16 bytes. Wait.
Okay, no, wait. 2 power 10 bytes is 1 kilobyte, right? This is 1024,
Yes.
right? And then 1 kilobytes is 1 megabyte, right? So 2 power 20 bytes is going to be 1 megabyte.
Okay.
Right? So it goes as orders of 2 power 10.
Okay, sir.
Yeah. Now, if I say 1 byte, I said is 8 bits. So if I want number of bits, then it goes as, so 1 kilobyte of memory will have 2 power 13 bits. Because it's 8 times 2 power 10 bytes, right?
Yes, sir.
Okay.
Excuse me, sir. Regarding
Yes.
the project, I have the railway
No,
crossing.
one sec. We'll come to that. Any questions on
Alright.
what we've done in class? If not, then those who are don't have any questions can leave. I'll close the lecture here. We'll continue on Friday. Then
So
I'll take
regarding this,
questions on
we
assignment.
have to consider the ROM as a black box